So here first question is the most stable conformation for the following compound is. So here we know that shade form is more stable, and the answer will be among these two only. For cyclohexane, shade form is more stable. The answer will be in these two only. And now we have to see which one is more stable. So here we have methyl group axial, and here we have methyl group equatorial. So as we know that at equatorial position there is no 1,3 diaxial interactions, but here we have a 1,3 diaxial interactions. Okay, so the answer will be this, but we have to see these methyl groups also. Okay, so because we have methyl groups are here, so when the methyl group is in equatorial position, so there will be a interactions between, there will be repulsions between these two methyl groups. So because of that reason this is unfavorable. Okay, so even though methyl group is at axial position here, compared to here, means like if the axial interaction means between the interactions between here hydrogen and methyl group, but here the interactions are between the methyl and methyl groups. So this will cause more instability to the products, to the structure. So because of that reason this is unstable and this is the stable conformation. So this will be the answer. And then next we have this question, following reaction is going through. So here we have taken this compound, it's upon treatment to Br2, and we got this compound. So here one named reaction is there, so that named reaction is called as Hunts-Dicker reaction. So in this reaction what will happens, so initially this will get ionized COO minus and Ag plus. Now we have a Br, so Br goes and attacks to this negative charge, and here some Br can exist Br plus as well as Br minus. There is a possibility to exist like this, and this Br plus goes and attacks to this Br plus goes attacks to the COO minus, and here we get COO Br, sorry, COO Br, and further here homolytic cleavage takes place, this bond, and then O minus, and here we have a Br radical, and again the elimination of CO2, here radical and this Br radical, both forms a bond, we'll get this final compound. So this reaction goes through free radical formation. And next important reaction is this one, the major product formed in the following reaction. So here we have CHO as well as a carbon ketone, and so the reagent is sodium borohydride in the presence of cerium chloride. So this is an important reagent, this is called Luche's reagent, and there is a some rules for Luche's reagent. Those, if you know those rules, then it's very easy to predict the answer. Like so this is the reactant, sodium borohydride in the presence of cerium chloride. So as we know that aldehyde is more reactive compared to ketone, because the carbonyl, this carbon is more electron deficient compared to this, because the plus I group of this methyl group. Okay, this we know that. So but when we have a sodium borohydride in the presence of cerium chloride, the condition will be reverse. So carbonyl ketone is more reactive compared to the aldehyde for cerium chloride, when cerium chloride is at that time. Why? Because so as we know that here cerium is in a plus 3 oxidation state. So this is, we can say this cerium chloride is a electrophilic reagent, we can say electrophilic reagent. So because of that reason, when where we have Br4 minus and the cerium. So like this, some electron density will transfer from Br4 minus to cerium. So because of that reason, the reagent also becoming electrophilic. Means like we cannot say electrophilic, we cannot say electrophile, but the electron density is decreasing here. So because of that reason, this has to react with the carbonyl carbon, which is having more electron density. Okay, here the more electron density is present in case of uh, carbonyl means ketone. So, because of that reason, so from this knowledge we can eliminate uh, this answer we can eliminate. Then this answer also we can eliminate, because Luche's reagent is not that fast, so where it can reduce both aldehydes and ketones, and the answer will be in these two. Okay, and here also, like sorry, in these two. So here we can see that this is selectively reacting with the ketone, not with the aldehyde, so the answer will be this one only. And the next question we have here, the correct relationship between the following compounds is. So here we have two compounds. First we'll see whether it's a mirror images to each other or not. So when we draw the mirror image for this, so like when we see this one in the mirror, so this carbon has to come here and this carbon has to go here, but this carbon position is not changed. Sorry, yeah. So here this this carbon came here and this carbon came here, and it is looking like first we will see the nomenclature here. So this will be first and this will be second, this will be third. So this is, yes, sorry, this is OH here, OH is there here, OH here also OH. So this is 1 2 3, 1 2 3, this is R, and similarly 1 2 3 4, and this is also R. So in the both the cases we have RR configuration. So there is a one rule that 1 and 2, if we do the mutual exchange, so this called as enantiomers. So when we do a mutual exchange of three groups, that is called as a homomers or identical. Okay, so this is a mirror image only, but the configuration is same here, R and R. So because of that reason we can eliminate the enantiomers. So since the both the configuration is same, we can go for the homomers or identical. And this one they just rotated by 180 degrees, that's it. And we just, you can follow this one only, because here also our configuration is there and here also our configuration is there, so this can be a homomers. And when we will rotate this one by 180 degrees, so we will get back to this compound. I am not explaining the detail because it's very simple only, and I have made a video on the toposity. You please watch that video so that you uh, will not be having any problem to solve this question. And another one, here we have sodium borohydride in the presence of methanol and THF. This is also simple reaction, like so here the product is mainly depends upon the how H minus is approaching, whether it is approaching from this side or this side. And here we have to see the bridged this methyl groups. So because of that methyl groups, the hydrogen cannot be approached from this direction, so it has to approach from this direction. So when it approaches from down like this, the hydrogen comes here and OH comes here. So this is the product, and here we have OH and H, so this is correct, but sodium borohydride cannot reduce this ester, so this we can eliminate, and this also we can eliminate because it reduces both. And here we can take this one, but here hydrogen is a hydride came from the above the plane, so this is also not possible. The final answer, sorry, this is H, so the final answer is remained is D. So these are the 2 marks questions which are asked in December 2015, I think.